So, binary search tree. New class, binary search tree. In the book, it extends search tree. That's fine, but I'm not going to make the interface. And so it has a private binary node E root, private comparator E C, private class binary node E. It has an E data. Should make that private. Private binary node E left. Private binary node E right. And then we want to implement the private void insert E. What's wrong? And I know this is what I told you to implement, but what's wrong with this method? It's signature.
Void.
It's a void, so you don't know if it succeeds or fails. Because can you insert the same thing into a binary search tree?
No, you're not supposed to.
You're not supposed to. So by returning void, you don't know if it's already in there. So it should probably return Boolean like the add method for the other collections to say whether it's successfully inserted the item into the tree. That's my fault. Should be Boolean. So let's fix that. And return false. Just for jollies, Java docket. So insert E, true if inserted, false if already in the tree. So, what do we do if the root is null?
Just put it there.
You just put the new thing there. So, I'm going to do that before I start my recursion.
Yeah, it should be your base case.
So, but it's sort of the base case. So if root equal null, root equal new binary node, and I'm going to cheat, and that won't be legal unless I go down here and say I need to create that constructor. Oops. Why are you busy? Public binary node E. Okay. So, if it is, I create a new node, its left and right child are null, and I set the top of the tree out. Else, I have something in my return true, right? Because I did insert it. Else, recursive insert E root. I return that. So now I need a private Boolean recursive insert binary
node, node, E, item. And it will return false. So, because of the way I wrote my first method, my insert method, know that I'm never going to pass null into my recursive method. That's what I'm promising myself. I'm not going to pass in a node null. Because I always want to point to, it's like in the linked list, you can't update. If you go past the end of the linked list, you can't update that, so you always have to point to the last node you're pointing at when you add to it. So we're always going to be pointing at the node that we want to add the left child or add the right child to. Otherwise, we don't have a handle to it. Now, you could change the recursive method to return a binary node and then do the assignment in the insert or above. Either way. So what I'm going to say is I'm going to compare. So int compare comp equals c dot compare node dot, and let's choose item. So I'm going to compare the item to the node, it's data, because I know I've promised to myself that the node won't be null. So I won't have a null pointer exception right here. What's wrong with this? Why are you complaining? There we go. Oh, silly me. So now I say if comp is less than 0, that means that the item is less than the node I'm looking at. So which way do I go? I'm going to go left. So I want to say if node dot left is not equal to null, I need to traverse left. I need to keep going. So I need to do recursive insert of item and node dot left. This is where I'm promising never to pass in a null into this method. Else, so it is empty, so that means I need to create a new node and stick it right here at the left side. Node dot left equals new binary node item. And I guess I should, I'm just going to say it's unchecked, right? Okay. Why is that? So I've solved the left side. Else, if comp is greater than 0, I need to go which way? To the right. So now I say if node dot right is not equal to null, I recurse item and I should actually fix this by saying return. Return true, right? So I return whatever the value of going down the left side, and then I also return going down the right side, else. So the right side is null, so node dot right equals new binary node E item return true. And if I'm not less than and I'm not greater than, then I'm equal and I can't do the insert, so I return false. Okay. Hardest question of the day. What's the big O of this? Of the insert method.
Log n.
I heard n, I heard log n. It's not n because I don't search the entire tree. I'm only going down the depth of the tree. Right? So each time I make that comparison, I go left or right. So I divide the problem in half. Right? I go left so many times, I go right so many times. So it's big O of log n. Now, there is a worse case. If the tree is a linked list, right? Everything was graded like I showed you. It was just A and then B and then C and then D. It is a big O of n operation. So worst case, it's big O of n. Average case, it's big O of log n. In this case, it's the average case. If you said worst case is big O of n, if you just said big O of n, that sort of doesn't show that you're thinking about that. You're sort of saying, I have to search every item in the tree. And this, the insert method, because it's a binary search tree, doesn't have to search every item in the tree unless it's constructed that. Yes?
But that's not really the average case, that's the best case, right? The log n.
The log n is the average case in general, right? If it turns out the tree, in general, the tree will be balanced, unless you have some weird way, if you sort the data before you insert it into a binary search tree, yes, you're screwed. But so don't sort your data before you insert it. But if you took just like English sentences or, population as you're sitting in this classroom, and I inserted you into a tree, binary search tree, then generally the insert would be log n.
I'm just asking to see if it's actually the average or it's like general. Just
It's not the average because the first one you insert,
no. I mean the log n. Is it like if you mathematically calculate, is it actually the average?
I believe it's not the average because there are, I don't know what n is, and then for every possible n, there's basically an infinite number of possible trees, right? Because n is just saying how many items to stick in the tree. So how those trees look is very different depending on how they go in. So I'm not sure that if you calculated the average of all those possibilities, you would get log n. But the idea is because when we do the insertion, we go left or we go right by cutting the problem in half, then that's why it's log n. And big O is not like an average, it's a mathematical formula. Yes?
So that tree up there, that's not a binary search tree.
Yes, it is.
It is a binary search tree.
Yes, it is.
So if we were to add ball to that,
Yes?
ball should be in between cat and owl, right?
No. Right?
So it could be
So I add ball. Is ball less than or greater than dog? Less than. Is ball less than or greater than cat? Less than. Is ball less than or greater than apple? Greater than. Put it at the right. And oh, by the way, the right is null.
no, that's fine, but so it's not going to go in between apple and cat.
Oh no. That's why I'm saying this. So when you're building this tree, it's completely dependent on how the items are, the order that they're inserted into the tree.
So you're never like reorganizing your insert, you're just adding.
A generic binary search tree does not get balanced. Now there are binary search trees that have the property that they're balanced, which then once you do the add, you rebalance the tree, so you reshuffle the things so that the depth of the tree is always trying to be log n or log n plus 1.
What if both the left and right sub trees are
If both the left or right,
Well, yeah, in that case, they were both null. So
if, well, what if I before I insert ball, I go down and I say, oh, I'm looking at apple, I make the comparison. And then which way do I do the insertion? I either go on the left if the thing is less than apple, or I go to the right if it's greater than apple. And then I would, again, if at the root is null, there's no left or right. I create a new root that has the value that I just inserted. Right? That's that one if statement at the beginning is if the root is null, I don't have to do any recursion. I create my node, assign root to the node, and I'm done. Else, I've got to then traverse the tree using recursion to get to the right place where I'm going to do my insertion. Yes?
So then, what would the parameters be to insert right side for cat? Or is that like
Right side for cat would be something like,
comments?
yeah, cod. Or, so anything that's less than dog and greater than cat. So, cod or cauliflower. Cycle. Yes?
So there is no inserting nodes between existing nodes in the tree. There's only increasing. You can only increase the length.
unless it's a balanced.
Unless the tree itself, once you do the insertion, because it is desirable to have a balanced binary search tree. Because then you don't get these long, dysfunctional linked list things.
To put ball in between apple and cat.
Right, no, it's a way of doing it, but that causes extra work at the insertion, because then you've got to rebalance after you do the insertion. And you don't have to rebalance every time, you have to rebalance when you notice it's a depth group. And it's good to have a balanced binary search tree, but it's more work in the insertion method. But you don't, because that would stop the case of the, this lame-o, right? This is a binary search tree. It's degenerate. Now you would say that actually if you were doing this, if you wanted balance, after you inserted C, you would say, hey, the depth is not right, it's too deep. Rebalance by shifting B up. And rebalance, I mean, there's ways of rebalancing. I think that's 311. It's actually also in the textbook. Wait a minute.
If you were to insert E to that, would it just go along with already?
Right, because let's say, I'm going to say insert E. Start at the root. Is E greater than or less than A? Greater than. Is it greater than B? Greater than C? Greater than D? D's right is null. Stick it here.
Also going to be done. So it's always going to be just one. Going down, it's not going to have a second branch of the tree.
In this degenerate case, because I inserted the items in a bad way. Right, if I change the way I insert things to say something like start with C and then a B and then a D and an A, the same four letters create a different binary search tree depending on how I insert them.
And this method is going to work with whatever is already existing and not bother with.
It's this particular one, because it's just a regular old generic binary search tree, doesn't worry about balancing, and it doesn't actually care if it's a degenerate tree or not. It's just, I'm going to stick it in where it belongs, and you guys are going to deal with it. How do you test this? Like, how would you test? One thing would be, depending on what other methods you have in this class, like you may want a size method, tells you how many items are in it. So I would insert some things into the tree, count, see if I got that number, insert a duplicate, size should not grow. The other thing would be have, certainly for your homework assignment, have a traversal, an in-order traversal, and make sure that each item is less than the next item in the in-order traversal.
Might add a method that returns an array list of e's that are sorted by doing it in order traversal. Then you could just say, 0 is greater or less than 1, and 1 is less than 2, and you could do that. You could also do make sure that there are no duplicates. When you do that insertion and the size doesn't grow, but what if they somehow deleted and duplicated, Another way to test it. But basically, the idea is that all the things to the left have to be less than the root, or the node at the top. And the easiest way to test that is by doing an in-order traversal and seeing that it's sorted. Yes?
I'm just kind of curious, why would you want to delete anything from a binary search tree?
The reason you would want to delete something is what if it's no longer important? For example, in our but let's say you wanted to have a binary search tree of contacts, the homework assignment. What if you no longer like this person? You got to keep them around for the rest of your life in your contact list? I mean, hey, things go away.
One contact created.
Yes.
So assuming we have in our tree example here, what would happen if you delete cat?
If you delete cat, it turns out you just move apple up.
Okay, so you just link
Because the deletion is basically take the smallest thing on the right and replace it. Well, there is no right, so then you move the left up.
So if we delete horse, then
Horse, you replace it with eel.
okay.
So, is there a type of method where you can take whatever is branching off the deletion item and then just resort those, or would that?
No, you just move them around. You don't have to resort them. You just have to figure out which one goes where. Yes.
And that's because all the other things are also attached, right? So
Yeah, it's like
and all the branches are still branches.
if we said this way, there's more to this, right? I could move eel and all the stuff below eel up into here.
But then what if Eel's got a rank?
No, eel goes up here, but then it's right. The book has the algorithm in it. I mean, the book shows how to do it. And when did the last time I read the book? 6 months ago. But basically, actually, it's not. You take the smallest of the right. So if we're deleting horse, we don't replace it with eel, we replace it with whatever down here is. The book has the algorithm, it's funky. And that's why I didn't ask you to write the delete, because the delete is actually, there's a lot of work because you do have to maintain the binary search tree nest of the binary search tree.
So you move dog with eel, since it's the smallest.
Yes. Because eel is still less than horse, and it's greater than cat.
But you keep checking the right side, the smallest of it.
What's the smallest of the right side of the thing you're removing?
So you replace dog with horse then.
No, the smallest. Eel is smaller than horse.
Oh, okay. The smallest of everything that's on the right.
Yeah. It's n log, no, it's log n. No, because you're just doing a swap,
Oh, yeah, yeah.
right? So you have to traverse to find the smallest. And that's a log n operation, because you're only going down one side. Well, you're going left, and then you're going right, and then left, 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 or choose right.
And the smallest will necessarily be a leaf node.
No.
No?
Because if I had a
Oh, right.
box,
But then what would happen?
I put eel here, and I move here.
Oh, then you have to insert fox and leave the location.
Well, fox gets stuck off the parent eel. No. If I do this, I get I replace it, I don't have colors, but this would be eel, horse, fox, zebra, no dog. Because I can, the right of this is less than that.
Okay, so you
By definition, because I had to go left first.
so you would swap eel with dog and then you would fox.
And
with
you
eel.
put fox, eel's right is now horse's left.
Okay. Okay, that's. I got it.
And that's why delete's complicated, because you gotta keep track of the node above the smallest one, because you gotta set its left to the smallest one's right. And that's why I didn't ask you to do that from memory. The book has it, and the book actually does a pretty good description of all this jungly moving around stuff. But and when you do this eel to dog thing, you don't mess with this node's left and right. You just change its data. And then you're not going to muck with this guy's left and right. You're just saying, this guy's right is now, this guy's left is this guy's right. Don't worry, because all the stuff that hangs off the bottom goes with you.
So then you get rid of the node that has the empty data now.
But it no longer, it's not connected anymore. It's like the linked list removed. It's floating in the ether. Right? There's nothing referring to eel anymore. The only thing that was pointing at the node eel is horse left. Horse left now points to fox, or the node with fox in it. No one refers to plural only eel.
What if you use cats with the entire subkeys?
If you remove cat, you replace dog's left with cat's left, because cat's right doesn't exist.
So that was what gets
Apple will move one up. Well, Apple and all its children. That's something else I should have mentioned for the midterm, and I'll talk about it again on Wednesday. You should know the names of these things. What's the root? Horse is a child of that. Cat and horse are siblings.
But cat and horse are also roots of their own trees.
They're also roots of their own trees. Before I delete dog, eel is a descendant of dog. Dog is an ancestor of eel. Yes?
If you move fox up to where eel is at, does that mean the node for fox is over null and then
No, the node for fox has two left and right, has a left and right nulls. It is now horse's left.
like you said when you move it up you just start changing data.
No. When I move whatever the least one up to the wherever it's being deleted, I just swap I overwrite the data. I then take the node that I just took the data out and copied. I then take that node's right and assign it to that node's parent's left.
Yeah, you don't. Yeah, because you want to have the nodes that are all connected to it follow.
Yes.
So you don't want to link.
So basically the rule for deletion is find the smallest item to the right of the node being deleted, swap that data to the thing being deleted, not even swap, overwrite. Take that smallest node's right branch and assign it to that node's parent's left. Obvious. And the big O of that operation is log n, because you had to do the traversal, the swapping and the moving and the changing of the parents left. That's all one. The The book has great code in it for this homework assignment. Can you delete multiple nodes? I would not suggest doing that because I don't know. You could write that method, but I would actually implement it by deleting one at a time. Because you want to guarantee the structure stays the same. I mean, that all like if you start deleting in the middle of the tree, you got to make sure that all the stuff goes up. And if you try to delete two things at once, it gets very hard to know where the link. But you don't know where the two nodes are in the tree, do you? What if one's at the top and one's at the bottom? So I would just, if someone said I want to delete multiple things from the tree, I would just loop over those things and delete them one at a time. Because otherwise, the function has to know too much about the potential structure of the tree, and there's too many possible structures for the tree. So you don't know where the items fall into the tree, right? Because you can say, delete the root, delete the root, delete the root, delete the root. Multiple times. But it's not, because the root changes each time you do the deletion of that item. Questions? Okay, so binary search trees are the same or different than binary search.
Binary search is like method or some sort of operation.
Binary search is a way of searching a sorted array by dividing it in half and half and half and half, right?
Actual data structure.
Binary search tree is a binary tree that has got a special relationship between the node and its left children and right children. So, is a binary search tree the same as a binary tree?
Well, it is an example of binary.
It is a binary tree with that special relationship. So it's sort of like, is a square a rectangle? Yes, but not all rectangles are squares, so not all binary trees are binary search trees. Binary search tree, depending on how you construct the class, is a binary tree, but the nodes to the left child are less than the node in whatever node you're looking at, and all the nodes to the right are greater than the node you're looking at. So the recursive definition is a binary search tree is a binary tree whose root may be null, or whose root is not null, and all the root's left child is a binary search tree whose values are less than the root. The root's right subtree is a binary search tree whose values are greater than the root. So it's a recursive definition. So know the difference, or be able to articulate the difference between a binary tree, binary search tree, and a binary search. Because they're different. I guarantee that question will be on either the midterm or the final.